Hello everyone, I'm glad in here to introduce our work, GeneralSparse, which is bridging the gap in SpMM for print large language model inference on GPUs. We will introduce our work in the following 6 parts. Let's begin from the first part. Currently, deployment challenges of large language models are brought by the growth of parameter size in storage and inference latency. In storage, the number of parameters of large language model has surged, doubling storage requirements and putting huge pressure on hardware. In inference latency, large-scale parameters lead to prolonged inference times, directly impairing the user experience. So, high storage demands and low latency pose challenges to the limits of edge devices and real-time applications. This is the network structure of large language model. We use prompts as inputs and get the outputs according to the decoder network structure. The network structure consists of repeated layers, and the details of each layer are shown in the figure. We analyze the inference process, then we find that there are 4 matrix multiplication operations, and they account for the majority of the inference time, about 18%. Then, recent studies find that pruning methods are key ways to solve this challenge in storage and inference latency. Pruning reduces network weights and maintains the accuracy of the results, reduces both the storage and amount of calculation. The gray is the network weights, and the red is the input embedding. We can see there are so many diverse print methods have been proposed here. However, SpMM remains the performance bottleneck as the figure shows. Although SpMM has a theoretical potential for higher efficiency, but in practical application, it has become a bottleneck, restricting the performance, occupying about 70% of the execution time. Then we will introduce the background and motivation. As mentioned before, weight pruning reduces computational and memory overhead, but introduces the sparse diversity. The sparse diversity mainly from 2 aspects. First, sparse patterns, and second, sparse levels. After pruning, the weight distribution is uneven, forming complex sparse matrix, which poses new challenges to computing architecture. For sparse patterns, we take 2 well-known pruning methods, random and magnitude. Random prune values randomly and resulting a uniform non-zero element distribution. Magnitude prunes values with smaller absolute values and leads to an unpredictable and irregular distribution. For sparsity level, for example, different types layers have different sparsity level requirements. Like this, recent study found that the bottom and the top layers shows higher sensitivities, so they require low sparsity level, but the intermediate layer have lower sensitivity, so they require higher sparsity level. However, existing SpMM solutions have poor adaptability and can't efficiently handle diverse sparsity. The traditional SpMM algorithms have the relative single design, so they are difficult to cope with the complex sparsity, resulting in low efficiency. And the sparsity are diverse, so they lead to the performance bottleneck. Here, there is an urgent need for an SpMM algorithm that can adaptively adjust to overcome the limitations of the existing methods. Next, we will introduce the SpMM, Sparse Matrix and Dense Matrix Multiplication on GPUs. The figure shows the calculation process of SpMM and the sparse matrix storage and the pseudocode. Then we analyze the computation process and consider 2 key aspects that affect the performance. As shown in the pseudocode, the calculation process of SpMM has 3 loops. One aspect is how to distribute 3 loops, M, N, and K dimension of sparse and dense matrix to GPU process units per parallel memory access. The other aspect is how to accumulate reduced intermediate results with reduction dependencies of key dimension. Because the most important thing about parallel computing is the correctness of the results. There must be no write-back conflicts. Inspired by previous works such as Botnick published at IC20, parallel memory access strategies can be abstracted as the process of dividing boxes in 3 levels of GPU like this. Sparse matrix and dense matrix are divided in block, warp, and thread level and integrated finally. So the memory access space is composed of many fine-grained box division strategies of the sparse and dense matrix like this. The sparse matrix have many fine-grained box division strategies like this and this. And this matrix is also divided in many strategies. These strategies finally integrated form the memory access space. And for different weight matrices printed by different printing methods, we can see strategy 1 and strategy 2 can obtain higher performance here. Then we find multi-level reduction algorithms can be used in combination for varied sparsity levels. We can see here, thread can use sequential reduction add to accumulate results, and in warp level, parallel reduction of shuffle can be used. Then thread and warp level can be used in combination, form this complex reduction space. Then we find for different sparsity levels, the thread warp and thread add warp, these strategies can obtain higher performance in different situations. Next, we will introduce the GeneralSparse design. We propose GeneralSparse, which automatically designs and implements high-performance SpMM program, as illustrated in figure. It consists of 4 parts: the memory access space, reduction space, the cost model, and the code generator. The pruned sparse matrix and dense matrix are initially processed by the memory access space and the reduction space through the cost model. For the optimal solution, the code generator generates the SpMM program. For memory access space, we propose the orthogonal dimension in sparse matrix division for diverse sparsity. We can see here, single and multiple row dimension means non-zero elements of single and multiple row in sparse matrix are processed by a worker, and the single row is beneficial when the matrix rows have distinct characteristics and require individual processing, and the multiple row takes advantage of the parallel processing capability. Parallel processing more elements. And the row non-split split means whether a row of the sparse matrix is split and processed by different workers. Row non-split means that there is no need to consider the communication of additional different rows. But row splits need to consider different rows, but which is beneficial from load balancing. For this matrix division, the computation on different columns of this matrix are independent, and only the elements in the same column are accumulated. So the dense matrix is distributed to workers with a uniform pattern of data block in column granularity. And unexport is the adjustable column granularity. We can see this group 1 column and this group 2 columns. The next is the integration between sparse and dense matrix. When adjacent consecutive threads process different columns of dense matrix, we can see here threads load the same non-zero elements in sparse matrix, but different column of this matrix, which forms the thread group. And this creates an opportunity for data reuse. We can use it by prefetching data into shared memory or using shuffle instruction. In order to cover a variety of sparse matrix division, we propose offsite abstraction. Offsite abstraction is a hierarchical approach with thread, warp, block offsites for sparse matrix division. We take the example of thread offsite. It indicates the starting position of processing non-zero range by thread groups, like this. 0, 2 is the non-zero range here, and this offsite abstraction can clearly locate positions of different rows and row segments, covering single multi-row and row split, non-split. In reduction space, the design motivation are here. First, reduction algorithm can be used in combination like this with the consideration of sparsity levels and the GPU hierarchy. Second, reduction algorithms need to align with the memory size space, especially irregular sparse matrix allocation. Here we simplify figure expression of the reduction algorithm just for better understanding. It depicts that two threads use multi and AND operations to reduce results of two adjacent columns corresponding with the same row. And here, reduction algorithms are designed from GPU hierarchy, so there are three levels: thread, warp, and block, and aligned with single multi-row dimension. Here, total is designed for single row. Here, a GPU parallel unit processes only elements in one row and doesn't cross row, so results can be directly accumulated and written back. Here, figure A shows the thread total. It uses the MAD operation and registers to sequentially reduce the results within the same row. And figure C shows the warp level. Warp total uses the warp level shuffle instruction and reduce results. And also black level, black total, use mul and AND instruction on shared memory to reduce results. Bitmap algorithm is designed for multiple row dimension. Here, a GPU parallel unit needs to process elements across rows, so it is necessary to determine the row number of elements to avoid incorrect accumulation of elements in different rows, like this. Thread 0 process to rows here, and each binary bit of bitmap represents a non-zero element. T represents the starting position of the row, and F represents the position within the row. Figure B shows the thread bitmap, uses the bitmap structure to determine whether a thread to continues accumulate the current results. If the next step cross rows, the result will write back directly. In warp black level, multi-threads perform reduction in parallel also. Besides, multi-level combination of reduction algorithms can be used on GPUs for diverse sparsity levels, which are aligned with row splits and non-split dimension. When a row is assigned to different parallel units, multi-level accumulation are required, and we design here many algorithms, but because of time, we will not elaborate it here. For automatic implementation, the cost model predicts the performance of strategies based on linear regression, like this. For training, we use the characteristics of the sparse matrix, like row numbers, column numbers, as the input for linear regression. We then use this model to fit the actual running performance of the sparse matrix. The code generator recursively constructs parallel loops to optimize memory size patterns. At the highest level, the SpMM kernel initializes the block level parallelism and perform block reduction, then move down to warp and thread level. Each part generates the corresponding code fragments. Next, we will introduce the experiment. Here is the experimental setup. The platform is NVIDIA A100 GPU and CUDA. The datasets include large language model print weights and sparse collection. And these are baselines we compared. They are classified in 3 classes: library, artificial designs, and auto-tuners, and sparse compiler technologies. In performance results, we obtained 20.82 speed up on large language model print weights, 6.39 to 7.46 speed up on sparse matrices, and 2.33 speed up on end-to-end large language model inference. Here is the performance of Pruned matrix, and we can see that we obtain performance speed up. This is the performance of Sparse Matrix. We can see we obtain performance speed up on different columns and different non-zero number range. On end-to-end model throughput, we can see speed up on model OPT 6 billion, Llama 65 billion, and Llama 70 billion models are evaluated. We can see that in different models, we obtain model throughout speed up. On end-to-end model analysis, we analyze the speed up reason. We can see GeneralSparse achieve lower inference latency, mainly because we replace the dense matmul with the more efficient SpMM. Next is the related work. We can see there are so many SpMM optimization works like Sparse and Sparse, and many works use tensor code to accelerate. For large language model, acceleration has become a critical research focus due to their growing computation demands, such as fast transformer, deep speed, and flash attention. And our work can integrate seamlessly with existing large language model accelerating frameworks. Next is the conclusion and the future work. The performance bottleneck of SpMM under diverse sparsity has been addressed through abstraction and automated design here, and our code is available at this. Thanks all co-authors. That's all. Thank you.